So I'm going to go through this lesson twice. The first time I'm going to do it, I'm going to show you how to do these problems in a way that's easier, but potentially takes longer. And then I'm going to go back through the 8 problems using, I don't even want to call it a shortcut, but something that requires a lot more thought, so the problems might go by faster, but technically it's a little bit harder to do. So if you want to just stick with the first round of the problems and hear me do it once and say that's how I'm going to do it, that's fine. Otherwise, listen to the second time I'm going through these problems, because I'm going to show you how to do these in a way that might be faster for you. Okay, so the first thing about today is we're going to go back to something we've talked about these symbols before. This symbol right here, before you came to Algebra 1, you called that a square root. You're not wrong. This is technically called a radical sign though. Okay, it's called a radical. That's the name of that symbol, radical. You cannot see that too far above. Radical. Now there are parts of a radical, you don't need to memorize this yet, but it is important to know that the little number sitting on the outside on the little ledge is called the index. And the number inside, underneath the radical sign, is called the radicand. It is what it is. That's what it's called. It's all part of a radical. Now there are 2 types of radicals we're going to be doing today. We're going to be taking square roots with square radicals and cube roots with cube radicals. Okay? There is a shortcut you need to know on your computer for when you type these answers into your Google form and or on Desmos. The TI-84 calculators that we have at the school have shortcut buttons for both cube root and square root that will look like this or like this. But on any other technology that you're going to be using, things in college like MATLAB, if you ever get to stuff like that in college, you're going to have to know the computer language for it, and these are what they are. If you want a square root button on Desmos, you type in SQRT, open parentheses, and it will make a square root sign for you. For cube root, you're going to do QBRT and make a cube root. Now these tables are already filled out for you. If you need to pause the video because you're writing this down along with me to write down these 2 tables, go ahead and pause it right now. These are tables that are going to help you do these problems for numbers that you see, because the square root of 1 is 1, the square root of 4 is 2, and on with these tables. So I have a table of the perfect square roots and a table of perfect cube roots if you need them. This will be more helpful, this table, for those of you that watch the video through the second time to take out the perfect cube and square roots. But for those of you who just want to learn the easier way, maybe longer, but technically easier way to reduce or simplify radical expressions, here we go. To simplify a radical expression, we're going to write the radicand, which is the number underneath the radical sign, in what's called its prime factorization. You may know prime factorization as factor trees. Not a table of factors like we did for factoring, but literally like a factor tree. What we're going to do is we're going to take pairs or trios out. So for those of you doing the first way, you're going to take pairs or trios out. Pairs for square roots, trios for cube roots. Okay, and then super important, if you have anything left over, which you will, you're going to multiply anything left over. Don't add it, don't divide it, don't subtract it, you're always multiplying your leftovers. Let me show you a few examples before you say, Ms. Quigley, I don't quite understand what you're talking about. Right. We want to reduce the square root of 50. Square root of 50 is not a perfect square, so it's not something that will come out to a regular number. If you were to type this into a regular calculator, it would give you 7 point ugly decimals. We have a better way to write these numbers to keep them more accurate without rounding. So what we're going to do is we're going to take this number of 50 and we're going to break it down into its prime factorization using a tree. 50 can be divided by 2 because it's an even number, which would make it 2 times 25. I can't break 2 down anymore, but I can break 25 down into 5 and 5. In this factor tree, since we're taking the square root, I'm looking for pairs. There is a pair of 5s. The pair of 5s get to pop out of the radical sign as a regular 5. So every pair comes out as one number. Every pair comes out as one number. So what I would do is I would write this one as a 5 in front of the radical sign, and anything left over goes back inside. So see how I did not circle the 2 and it's at the end of a branch? The 5's got circled because they're a pair, but the 2 is by itself, so it stays under the radical sign, and that is the simplified radical form. Let's do the same thing for number 2. Okay, I'm looking for the square root of 24, so I'm looking for pairs. 24 can break down into the following. Oops, that's an ugly tree. Let's try again. 2 times 12, 2 times 6, 2 times 3. Y'all see how I'm breaking down the numbers till I can't break them down anymore? Nothing besides 1 and 2 make 2. These are all prime numbers. So its prime factorization is 2 times 2 times 2 times 3. I'm looking for pairs of numbers because I'm taking the square root. There's a pair of numbers. Are there any more pairs? No. So I'm going to take that pair of numbers out as a singular 2, and underneath the radical sign, underneath this square root, I'm going to take all of the leftovers and multiply them. My leftovers at the end of my branches are 2 and 3, so they go underneath the radical sign and they're going to be multiplied. This would be 2 square root, or radical 6. That is the simplified radical version. It's equivalent. These are the same, but it's simplified. Now, number 3 and 4. If you look at those, am I still taking the square root of those numbers? No, if you look, I'm taking the cube root. So instead of pairs, how many in a group for it to come out? 3 in every group. Let's start breaking down 162 to see what we get. 162 will break down into 2 times 81. 81, well, that's 9 times 9. And then 9 is 3 times 3. And 9 is 3 times 3. All of those numbers at the ends of the branches are as simple as I can get them. I'm looking for trios. Here's a group of 3 numbers that are all the same. That trio is going to come out as one number. The trio comes out as one number. So in front of my radical sign with a cube root this time, remember we're doing cube roots, would be 3, and then the leftovers go inside. Oh, I'm not done yet. I almost boxed that answer. This would be we'd have to actually multiply these out. Come on, squiggly. 3 times the cube root of 6 is the simplified radical form. Now that we've seen a couple examples, I want you to stop the video and I want you to try number 4. Remember, we're taking the cube root, so you're looking for groups of 3 when you break 48 down. So when we break 48 down, we should have 2 times 24, 2 times 12, 2 times 6, 2 times 3. That's a lot of 2's, but we're looking for trios of numbers. Here's a trio of 2's. That trio is going to pop out as one number in front of the cube root. Anything else that is not circled gets put back underneath the radical sign and multiplied. This cube root of 48 reduces and simplifies to 2 times the cube root of 6. Now, if I were trying to write these answers online in my Google form that you will do after you take this or watch this video, and or on Desmos to check my work, I'd have to write it a little bit differently because the computer doesn't do the cool radical sign. So if I were writing number 1 as an answer on Google Classroom, I would type 5 SQRT open parentheses 2 close parentheses. Whoa. Yes. 5 times the square root of 2. If I were writing number 2 online, I would write 2 times the square root of 6. 2 times the square root of 6. Do you see how that translates? The green is how I would write it in a computer for the boxed answer. For number 3, the way that I would write that is 3 times the cube root of 6. 3CBRT, open parentheses, 6, close parentheses. And for the last one, let me move my face because I know I'm going to be in the way. There it is. For the last one, I would write 2CBRT, cube root of 6, close parentheses. 2 times the cube root of 6. Now let's talk about numbers 5 and 6. Those are the only ones that we're going to do. We're going to skip number 7 and 8 because I know you're already tired of listening to me talk. On number 5 and 6, there's already a number in front of the radical sign. Do y'all see that? See how on number 5 it's 6 times the cube root of 64 that I want to reduce? That's okay. That 6 will just be in the front when I start reducing the whole problem and multiplying everything together. So for right now, I just kind of ignore it. I ignore that there's a number in the front, and I break down like I know it. Now we are looking for trios because it's a cube root. 64 breaks down to 2 times 32, 2 times 16, 2 times 8, 2 times 4, wow, and 2 times 2. That's a lot of numbers, but I remember I'm looking for trios for the cube root. There's a trio of 2's, oh snap, and there's a trio of 2's. That's fine. Is there any number that I didn't circle at the end of the branch? No, so there's not anything going to be written anymore underneath the cube root sign. So when I'm starting to answer this, it would be 6 times the first group of 2's times the second group of 2's with nothing left underneath the radical. The radical disappears. But that 6 that I ignored earlier, I put at the beginning of my answer. 6 times 2 is 12. 12 times 2 is 24. So 24 is actually the simplified version of 6 times the cube root of 64, because there was 2 trios of 2's underneath that radical sign. Sometimes it happens that the radical will disappear. Let's try number 6. Okay, we'll still do this one together. Now, what number is in front of the radical sign that I'm going to ignore for a hot second? A -1. Very good, if that's what you said. There is a -1 in the front, and we're taking a square root because there's an invisible 2 right there. So I'm looking for pairs of numbers. Let's start breaking this down because I'm ignoring the -1. 2 times 144. You'll see how I usually start with 2. It's a little bit easier to break it down when you're using small numbers. So start with like 2, and then if 2 doesn't work, try 3. Then try 5. 2 times 36. 2 times 18, 2 times 9, 2 doesn't go into that, oh, but 3 times 3 does. Now remember, I'm looking for pairs, so let's go in and let's circle some pairs. There's a pair of 2's, oh, there's a pair of 2's, and there's a pair of 3's. Is there anything that's going to be left underneath my radical sign? Yeah, there's a 2 hanging out right here at the end of a branch that didn't get circled. So there's still going to be something underneath my radical sign. It's going to be that 2. So let's see what we have. We have that -1 from where I started. Then I have the 2, a 2, and a 3. And then underneath the square root, I still have a 2. Oh, you can't see that because my face is in the way. There we go. Anything that I pulled out or is left over gets multiplied together. -1 times 2 is -2. Times 2 is -4. Times 3 is -12. Throw that in a calculator if you don't believe me. So -12 times the square root of 2 is how I would answer or simplify negative square root of 288. If I were trying to write this on a computer, I would write -12 SQRT 2, the square root of 2. Okay, if you're good, if you feel fine, and you don't want to watch the second way to do these problems, go ahead and stop the video now and go to the form. If you're like, I'm ready for a challenge and I think I can handle the other way to solve these problems, I'm going to go back through all of these notes one more time. But I'm going to show you what could potentially be called a shortcut. It's just different math. Okay, so we're still going to write the radicand in prime factorization. But this time, if you can write it in prime factorization, but find perfect square factors or perfect cube factors, which are from the table, perfect square factors and perfect cube factors, if you can find those, then you can take a shortcut. Here's what I mean. Look at number 1. It's a square, so I'm going to be using the perfect square roots table. And if I break it down like I did on the other page to 2 times 25, because that's 50, isn't 25 on my table? 25 is on my table. I know immediately that that's going to pop out as a 5 because it's a perfect square root. So I could stop right there and I say, I have a perfect square. That perfect square is going to come out as a 5, and anything left over stays underneath the radical sign. That's the same answer I got on the other page. It's just faster. It's using perfect square roots table and the perfect cube roots table. Now there are times that this won't happen, especially if you use 2's to break things down. But if you look at number 2, 24 we can break down to 2 and 12, but if I start looking for the perfect squares, can't I break this down to 4 times 6? And 4 is on my table. So I know immediately that that 4 is going to pop out as a 2, and I can be done. 2 square root of 6. Done. Now, cube roots work the same way. If you start breaking down the cube root of 162, some of you may not know how to break down 162 without starting with 2. That's fine. If we start with 2, this is going to be 2 times 81. Okay, 81 still isn't on my table because I'm looking for cube roots. So I break it down again, 9 times 9. And you might get excited because you're like, oh, 9 is a perfect square. But remember, we're looking at perfect cubes. Those numbers are not on my perfect cubes list, so I can't use it yet. But you could break them down to 3 times 3 and 3 times 3, and then find your trios and have 3 times the square root of 6, 2 times 3. So sometimes the perfect square table is going to help you because you'll be able to find the perfect square or perfect root. Sometimes you won't stumble upon it and you'll have to go back to the other way of breaking it all the way down and looking for pairs or trios. Okay, I want to jump, and I just covered it up, so let me erase this for a hot second. Number 5 is kind of a funny question. Number 5 was the one that came out to a straight up number instead of a radical sign. So if you look at number 5 there, it's 6 times the cube root of 64. Cube root of 64 is legitimately a perfect cube, so we don't even have to do any work. We know that this whole thing is actually 4. The cube root of 64 is 4, and I can therefore just say that this is 24, which is again what I got when I broke it all down. Looking at number 6, the square root of 288. 288 isn't on the list of perfect squares, but if I break it down to 2 times 144, my noggin should be going off because the square root of 144 is on the list. 144 is 12. So this is going to be 12 square root of 2 with that negative 1 still in the very front multiplied. Negative 12 times square root of 2 without all the work I had to do in the other way to break it down to its actual prime factorization. As with the last lesson, if you actually want the breakdown of all of these notes, including number 7 and 8, Ms. Jackson's key will be uploaded to the form as well, so you'll be able to copy down the rest of them if you want. We empower, we impact, we love. We are Skeeter Nation.